first thing we're going to talk about is a game theory. And this we're going to build a foundation of a multi-agent system, therefore ultimate multi-agent learning. Okay, just bear with me, put it in the right place. Yeah, so what is a game theory anyway? So game theory is it's sort of a, or why game theory? So the game theory is why we need a game theory is that although we're dealing with computational systems, or although we do all these computational problems, right? However, in all these systems, all this computerized system, they also have this social or economic transaction. So when I say social or economic transaction, meaning that you might have multiple people involved, multiple AI systems involved, and they are mediated through the internet, through those computations. The example would be, for example, say you have this Amazon, okay? In the Amazon, you have users, you have end users, you have these vendors, right? The people put the goods online. You got Amazon, you got advertisers, right? You got all these people, they have a different sort of incentive. They make they're using their AI system to help them to, for example, make predictions about user intent, make a forecast, and also in advertising, as I said, they make a bidding, right? Try to sort of target to the users and looking at their ads, try to maximize their revenue. And obviously Amazon try to maximize their own revenue, right? And users try to sort of find the relevant content or buy the stuff from them. So they all mediated through this computation. And so in fact, we could say those computerized system is also economic system, because precisely as I said, there's multiple parties and usually they are self-interested. So computer science is working on the study of the representation of process of information. That's a key part of it, right? And for certain tasks. But economics is really working on the decision making that made by multiple parties. So when they multiple parties looking at their preference, capability, information they have, and motivation. So these multi-agent AI really need to take into account these two aspects of problems and combine together. So it's a multidisciplinary study, right, with economics. So in underlying theory, one of the theory behind economics is really game theory, right? Computer science, we are focused on is machine learning. So that's the combine these two is this module is about. So we're going to talk about today is game theory as some of the basic concepts. You will be able to understand, what is Nash equilibrium. Okay, and so, sorry, I need to close this pop-up. Ask me to update. Okay. Chrome. I need to update that. Okay. Just a moment. Sorry. Yeah. So the you will be able to understand some of the concept of Nash equilibrium. These are quite important ones, and then we also looking at some of the math behind it. So in other words, we're looking at some of the proof of the existence of the Nash equilibrium. And also we're going to looking at some of the practical cases when we're talking about the interactions between different sort of participants. So bear in mind here, we're still not talking about machine just yet, but we were talking about people, right? The incentive between them, how they sort of coordinate together. But this these concepts, the technical, things are hugely important for the later stage of this module when we're looking at this sort of agent. So the game theory is really try to looking at a situation where you got multiple participants. Let's say in this case is players and people, and it could be this agent in the future, right? Then they're gonna interact, affect each other's outcome. So in 17th centuries, and people actually already try to think about optimal solutions for some of these card games, and this modern treatment of game theory starting from von Neumann from 1928, before computer science, in one of his famous books, actually talking about introduce this sort of game theory and the min-max kind of formulation of some of the game. And in fact, the interesting thing, if you're looking at this sort of mathematical development of that, in fact, the people in this optimization community talking about linear programming and the duality of this sort of linear programming is in fact equivalent to this min-max kind of formulation that von Neumann did that. But I think only later sort of people discovered the similarity between them. But when we're talking about the solver for this min-max game, actually we're going to talk about this duality stuff. So more than 10, so it's quite important sort of area. In fact, if you're looking at these Nobel Prize winners for economics, there's a lot of in fact contributes heavily on game theory, starting from Nash, Jun Nash, and in fact this year, sorry, it's not this year, last year, 2020, the 2 Nobel Prize winner, the war in fact came from game theory community. They were in fact working on this auction theory, and which we're going to talk about in mechanism design. So give me an example. Suppose that you study exam or presentation for a course. You can only study either of them, right? You can put your 100% effort on, focus on the exam or focus on presentation. So presentation is that you need to jointly work with another student. An exam, you could do it alone, okay? So obviously you want to maximize your average grade. So let's say 50% will count for exam and 50% count for the presentation. So your partner have the similar choice, okay? So we can looking at those results, those reward. If you study for exam, you will get 92. Say you put the majority of your time, sorry, most of all your time on the exam, you get 92. Otherwise, you get 80. But you can also spend your time not on the exam, but on the presentation, work together with another guy, okay? If both prepared, then each of them you get 100. If one of them prepared, then the presentation would give the work would contribute to 92, right? But if none of you prepare, because if all of you could sort of go for working on exam but not working on presentation, then both of you would get 84. So you are not allowed to communicate. How do you make a decision? You know all this information, right? And now it's time for you to decide what you're going to do about this situation. So you need to take into account what the strategy of your partners, because obviously if they were preparing exams, they're not working on the presentation, only you working on presentation, then obviously it's good and not good for you, right? On the other hand, you would hope your partner to put their time on presentation, and maybe you can focus on exams to getting your higher mark or both of them, therefore the averaging one you have. So everybody are quite selfish. If everybody thinks that way, perhaps nobody gonna working on a presentation. So how can we mathematically rigorously to study this? One way to looking at it, to put all the information, okay, in this in a matrix form. So this is sort of illustration here. Then you have yourself which is we call it as sort of role player, right? You got this column players, which is your partner. Each of you has two choices, either presentation or do exam. Okay, so we define this as a strategy. So wait a minute, I'm gonna turn on the light. So so this is sort of your choice, which we named as a strategy. So later we'll explain exactly what strategy means. At the moment, you can consider the strategy just as the action. We got two choices here. And then we can write down this payoff. So the payoff or the reward is basically how much the expected grade you will get. For example, if you and your partner working on presentation, okay, then this expected grade for yourself gonna be 90. So the 90s came from the fact that you both of you do presentation. Therefore, that's looking at this sort of rules that when you both of you do presentation, then none of you are gonna start the exams. Therefore, you would get the smaller sort of a grade, which is 80 for your exams. And because both of you study presentation, therefore, everybody gets 100. So if you're looking at this, because 50% is 80 and the 50% goes for the presentation, which is 100, that is, you got this overall grade, which is 90, okay? Then equally your partner will do the same. So you can apply this sort of a rules to each of the cases, like exam, presentation, exam. Then just for you to verify that, whether that makes sense or not. So once you got this payoff matrix, what we call the payoff matrix, and then you can base on that to make a decision. So my question is, without looking further of the slides, if you were participating on this, what would be your decision? Is anyone can answer?
The exam.
Exam? Why? Anyone can provide explanation?
A couple of people are answering in chat. I'm not going to take any credit for that, but they're saying it's most likely safer.
Sorry, could you say it again?
A bunch of people are answering in chat, and I'm not going to take any credit for this, but they're saying that it's most likely safer.
Safer, okay. So safer means that they would, if other people do exam, then you basically, okay, let's see whether it's safer. Okay, if you taking exams, otherwise other people do presentation, what would be your score? Actually, you could better off, actually, isn't it?
I think if you look at the expected outcome of doing the exam, regardless of what your partner does, that's higher than the expected outcome of doing the presentation, regardless of what your partner does.
Okay, you're looking at these sort of expected ones regarding to other people.
The average of 92 and 88 is higher than the average of 90 and 86.
Okay, yeah. Without knowing this, your partners, you're taking the average. But the weight, why average? Why you're taking equal rate? I think that wouldn't sort of because it's not that 50% chance that your partner gonna do the exam, right? 50% chance your partner gonna do a presentation, isn't it? if that's the case, then I think that the rationality, that rationale might,
yeah, that's true. That's true.
Yeah.
No matter what my partner does, I'm always better off taking the exam.
Okay, no matter what other does.
Like, no matter what he does, if I take the exam, I'm better off. So I'll take the exam. If I'm selfish, obviously.
Okay, no matter what other people does, and if I do that, then I'll be better off. So yeah, so I think what you can, when you say better off, is actually looking at this way. So yeah, one way to looking at this, I think it's always sort of, all these things is really sort of to encourage people to have a strategic thinking. So suppose that we're looking at, yeah, I'm not sure whether I can, yeah, I can do pen. So suppose we're looking at this presentation. So let's say your partner do presentation. In this situation, which choice do I have would be better off? I would take exam, right? Because if I do presentation as well, I will get 90. If I do sort of exam, I will get 92. So in this case, doing exam is better off. So equally, if the partner would decide to take exam, I would also better off, because if I do presentation, I will 86. If I do exam, I will be 88. So I think I was still better off. So in this case, no matter what other people do, I will be better off in the sense of, you know, compare with the another choice that I got. So in this case, I think that would make sense, isn't it? Okay, I'm gonna looking at this chat to see is any sort of you can looking at a maximize the minimum value you can get. So yeah, I think it's definitely interesting to looking at this kind of min-max can assume your partner take the best strategy for them. Yes. So that's the very good point, is that we need to assume that they need to maximize their own. So in other words, we think about all players, they are rational. In other words, they're going to maximize their own sort of, yeah. Yes. Yeah. Okay. Sounds good. So this is sort of give you a way to sort of, you know, test it out. Understanding of my son is here, so it's a Ting Ting. Be quiet, okay? Yeah, so this is sort of an example. Let's look at another example. Okay, before that, so what will happen in this game? Yes, I think everybody, you know, answers correctly. That exam, it seems that it's a single study for exam is safer. So the safer is really about, you know, better off compared to, you know, the other choice of yours. Okay, so how are the players like to behave? So I think what the key question we're going to answer in a game that's setting like that is really try to see the behavior of others, try to understand the behavior of others. And in order to really do that, we need to have some assumptions. For example, the payoff is only things that we need to consider. And the players know all the possible strategies and payoff to others. In other words, they know the payoff function, the payoff matrix that I specified. But in practice, it may not be true, right? Because you don't really know the reward, yourself the reward, but also other result. So sometimes you need to try the error. So that's the place you need to, you know, make use of learning, make use of machine learning for that. But we're going to talk about later. But for now, we just consider we know all these sort of, you know, rewards that we see in each of the, you know, action. And also we consider players are rational. So each players, they try to sort of maximize their own payoff, and each payoff succeed in become optimal strategy. So the the example that I show, in fact, each player, in fact, has a strictly dominant strategy. So in other words, this exam strategy would be strictly better than any other option. When we say strictly better, is that no matter what other people do, I will be better off than alternative choice that I got. So in this case, we fulfilled what we would do on this game is that we would be able to predict the outcome. So it's because all these things about the game theory, why we need to really understand some of the strategy is when we say better, is that we able to sort of based on this assumptions, they are rational, and we know they're going to do that because they're going to optimize that. Therefore, this is their certain optimal choice with respect to their own objective. Therefore, we would able to predict the outcomes. So, interesting thing is looking at this. If you from the single agent perspective, right? From a God perspective, there's someone know these things. If they want to coordinate, they would certainly say, okay, you guys should prepare presentation, because if you do that, everybody would get very good marks, very high marks in this but there's when nobody coordinate this, then they end up in this unfortunately bad situation. Exam everybody get 88 grade rather than a 98. So I think that's interesting things make this sort of a game theory very interesting compared to the single agent solution. So that's why we have this a field called game theory to understand, and also this mechanism design field where it's try to design the game in such a way to encourage people to behavior, so that that kind of behavior is also socially sort of socially maximized. So in other words, they want to say, okay, maybe the 1990 outcome is something everybody would be better, but how can we design the reward in such a way, in the end, the individual, agent or player, they try to maximize their own objective, and they also reach to that kind of goal. So I think that's sort of a mechanism design is really about, is really try to design the game in such to fulfill that kind of task. So you can think about this kind of inverse version of this game theory.